questions? Okay. Any?
One of our friends. We give a couple minutes.
Super. For waiting 2 minutes, is there a washroom?
Yes. Right. Come è andato la lista? Che riceve con Francesco.
Già io la scorsa volta.
Puoi chiudere il microfono. Uscire.
Penso che puoi mutare tu una persona.
Sì, ma non la posso mutare, non la posso mutare, quindi vogliamo riuscire alla presentazione. Il silenzio per i puoi passare invece il volume, forse tu no.
Non sa più.
Giusto perché ho amplificato. Comunque, almost ready. Okay, I think it's a good time to start. It's really a pleasure today to welcome Professor Nicolas Cowan with us. He will give us a seminar shortly, but first I have to provide a very long introduction because he's a foremost expert on solar planet atmospheres. He's a graduate student, he did his current studies at the University of Washington in Seattle. And then since 2015, he is at McGill University in Montreal, Canada, now as an associate professor. As I mentioned, he is heavily involved in solar planet atmosphere work, and among the countless big involvements he has, I can, for example, mention the co-chairship of, on the Canadian side of the Ariel and 4 mission, and strong involvement in ZST, future big NASA telescopes for planetary system characterization, and for ground, for example, involvement in infrared high resolution spectrographs such as NIRPS and SBO. Today, the topic of this work will be focused on atmospheres of planets.
All right, thanks for the for the invitation, the opportunity to come up here and give a talk. It's beautiful. I always love coming to Italy. The architecture is nice, the food's great. I'm just very happy. Okay, so the work I'm going to present today is all stuff done in my research group at McGill. So we have a snazzy acronym and logo, basically because it was like, you know, I had to like pay an undergrad to do this, and she was very good. So basically we use space telescopes, and increasingly I'm trying to get into high resolution spectroscopy from the ground. But mostly we use space telescopes to try and characterize the atmospheres of exoplanets. So in practice, these are the people who do the work, and I mostly apply for funding. And so I'm going to highlight some of their work, So I'm in two different departments. Half of me is in Earth and Planetary Sciences, which is EPS. That's the brown people are associated with Earth and Planetary Sciences, and the purple people are associated with the physics department at McGill. So I'm a professor in both departments. And then I also work with a lot of undergrads from computer science because I like good coders, and atmospheric and oceanic sciences because turns out, atmospheres are atmospheres. So Earth atmosphere people sometimes get curious about exoplanet atmospheres. Okay, so I'm sort of preaching to the choir here, but just like super quick recap. In the 90s, this is the planets we knew of in orbital period and planetary radius space. There were no planets on short period orbits. There was nothing interior to Mercury. So we didn't know of any planets with, a few day orbits, a couple hour orbits, even weeks orbits. These didn't exist. Now we know that nature not only can make these planets, but actually likes to make those planets and arguably prefers to make those planets compared to planets like the solar system. So these short period planets are actually more common. They're not just easier to detect, they're actually more common than things like, Jupiter in a Jupiter-like orbit. So that's cool. So then there's basically two questions you can ask yourself at that point. One of them, which I'm not going to touch on, is how do these planets form? That's very interesting. And then the other one, which I am going to touch on, is what are these planets like today? What are their atmospheres like? What's their climate like? What's their surface like? What would it be like to be on one of these planets? And so we can try and make some predictions about this, just given basic kind of atmospheric physics. So the first statement we can make is that we expect these planets to be hot unless they're orbiting a cool star. And I'm not going to talk about the ones orbiting cool stars. Those are interesting. Those are like your habitable, things like the TRAPPIST planets. Planets on like a 1 week orbit around a ultra cool red dwarf star can actually be habitable. That's exciting. I'm not going to talk about them today. The observations are kind of like, there was another Nature paper last night basically saying like, maybe this thing doesn't have an atmosphere. So like, I want to talk about atmospheres. And so I'm going to stick to things that actually have atmospheres, which are, kind of bigger planets. Okay, but we think most of these objects are going to be hot. And the other thing we can expect is that they will be synchronously rotating, which means they're going to be tidally locked into a state where they have a permanent day side and a permanent night side, as long as they're on a circular orbit. If the planet's on an eccentric orbit, they can't be synchronously rotating, and then you get other things that are more interesting. But for most of the planets, I think today I'm only going to talk about planets on circular orbits. So we're basically always going to assume that they have a permanent day side and a permanent night side. So these are basically the two main differences with the planets in the solar system. I should mention, I've had a high espresso to food ratio this morning. So if I'm speaking too fast, just like stop me and interrupt me and ask questions. If I say something and you're like, I missed that word, or like you're saying something that makes no sense, please just interrupt me. This is a small enough group. I think the people online is maybe a different matter, but people in this room, just interrupt me. Okay, so I'm only going to talk about two classes of planets today in the interest of time. I'm going to use hot Jupiters as sort of like an introduction, because we sort of kind of understand hot Jupiters. Not really, but I'll use them as an example. And then I'm going to skip all the things in between, which are very interesting. I mean, there aren't very many planets here, but these are really cool planets. And I'm going to talk about lava planets, which are down here. So I'm basically going to go from giant, really hot planets to small, rocky, really hot planets. And then I'm also interested in these, planets orbiting red dwarf stars. But again, in the interest of time, I'm not going to talk about today. If you're interested, you can ask me. I have opinions, I have thoughts, I have students working on this. But like I said, so far, all the spectra and everything are kind of like flat. So we're not learning a heck of a lot about these planets currently, but there's fun theory work to be done on those planets as well. Okay, so hot Jupiters. So you take Jupiter, you stick it close to a star. What might that look like? And to keep things simple, I'm going to focus on exactly one specific hot Jupiter, WASP-12b. And yeah, so I'm just going to show you some examples of observations taken by other people, taken by my group, all related to this planet, and just as kind of like a test case of what we can hope to learn with space-based observations of this planet. And so these are the tricks of the trade. These are how we characterize short period planets. There's the transit, which everyone knows about because that's often how we discover these planets, but you can also do transit spectroscopy. There's eclipses, which happen half an orbit later when the planet passes behind the star. And I'll talk about that a little bit more. And then there's phase observations, which I personally I love phase observations because you get to see all the different parts of the planet as it kind of swings into view. It also means you have to stare at the planet for an entire orbit, which is not really feasible for any planet in the solar system, but for exoplanets that are on like a 1 or 2 day orbit, this is actually doable. Okay, so let's start with the transit. So you do a transit, try and do transit spectroscopy of WASP-12b, and what do you see? These are observations taken with the Hubble Space Telescope with WIFC-3. So this is work by Laura Kreidberg, so I was not involved in this, but this is sort of just like setting the stage here. So this is your transit depth as a function of wavelength. And what you should take away from this is basically it's flattish. So the planet has a certain size. And then when you get out to around 1.4 micron, the planet seems to be bigger. And of course, the planet's not actually bigger at that wavelength. It's just that the atmosphere is more opaque, right? So you go from having a relatively transparent atmosphere to a relatively opaque atmosphere. And any spectroscopist can tell you that water vapor is absorbing near 1.4 micron. And so the conclusion from this is that, okay, this planet has water vapor, which is increasing the opacity of its atmosphere around 1.4 micron. At least it's got water vapor near the day-night terminator of the planet, which is what we probe in transit. Okay, so again, in transit, you're seeing this annulus, and it's at a very specific location on the planet. It's not the day side, it's not the night side, it's right in between. Okay, so that's what the transit shows. You see water vapor. Let's look at the eclipse. So this is work by Kevin Stevenson. Again, not my work, but a great compilation of lots of previous studies from the ground, in the near infrared, some WIFC-3 emission spectroscopy going out into your Spitzer, IRAC, photometry. And the takeaway from this is that the day-side spectrum, which is basically what you measure with an eclipse, you see the day-side emission spectrum of the planet. The day-side emission spectrum is basically consistent with a black body. It's a hot black body, so that's exciting. It's like almost 3,000 Kelvin, so that's super fun. But there's no sign of water vapor in this. And so now you're this is a confusing story because this is the same planet, right? So on the day side, it doesn't seem to have water. At the terminator, it does have water. This is emission. You're seeing thermal radiation from the planet, but you can repeat this experiment with reflected light. So now you go to shorter wavelengths. You kind of go off the left side of this plot. All right, so this is also using Hubble, but in this case, we're not in the infrared, we're at visible wavelengths, and we're trying to see reflected light from the planet. So this is actually work that my PhD student Taylor Bell did. So these were basically our two scenarios going into the observations. We had one scenario where the planet was going to have day-side clouds, hazes of aluminum oxide. So aluminum oxide is notoriously white. Well, it's actually kind of gray. Looks like that. This is actually the stuff they put in sunscreen. So that's why sunscreen looks white. It's good at, so we figured this would be good at reflecting light. Okay, so this was our kind of high albedo scenario where the planet would look very reflective at visible wavelengths. And then we had a blue sky scenario where you had a cloud-free atmosphere. So the reflected light would look blue like that. So that's what we expected, one of these two scenarios, and we convinced ourselves the error bars were small enough we'd be able to differentiate between these two scenarios. And instead, what we got were basically upper limits at all wavelengths, most of which ruled out both of these scenarios. In other words, the day side of this planet is very, very black. Okay, it's not just, it's not even blue or gray or whatever. It's just the day side is black. And it turned out the model that could finally make sense of this was a scenario where the day side is not even molecular hydrogen. The day side of this planet is basically atomic gas. It's atomic and actually like ionized species. You get things like H- creeping in. Okay, so basically the day side of this planet kind of makes sense. The temperatures we're talking about, 3,000 Kelvin, is basically a typical M dwarf star. Okay, so the day side of this planet, when we first set out to do this, the models we were using had a heritage in the solar system. These were people who'd taken a model of Jupiter and they kind of turned the knobs on it and then made it try and make it work for a hot Jupiter. But the reality is that the day side of this planet is more like a star. And so you actually do better taking a stellar model and turning some knobs to make it be more like a hot Jupiter. And so in the end, the opacity sources you see on these very hot planets, at least on the day side, are basically stellar opacity sources. So it's atomic gas with some H minus. Okay, so then this is sort of a cartoon view of what's going on, putting all these things together. So the day side, you don't see water vapor, and part of that is that there actually isn't much water vapor on the day side because it would be photodissociated. There's in fact not much hydrogen gas. It's mostly thermally dissociated on the day side. It reconnects, the hydrogen gas reconnects recombines into molecules as you swing towards the night side, and you also see more water vapor there. And there's a couple of points to make here. One of them is that even if there is water vapor on the day side, you're not going to get strong emission features, basically because the day side, you get a weak temperature inversion. So essentially the vertical temperature profile on the day side is going to tend to be quite isothermal, which means even if there are molecules there, they're not going to give you interesting emission or absorption features, right? So this is sort of like the bane of emission spectroscopy, is a vertically isothermal atmosphere. And that's basically what you expect on the day side. If you're lucky, you might get a strong inversion, and then you would actually see water vapor in emission, but that's basically not what we saw. So that's the first point, right? So basically, you don't expect to see water or really many spectral features on the day side. In transit, you might see water vapor. And then the other important point is that this hydrogen, going from atomic hydrogen to molecular hydrogen, is an amazingly energy-intensive reaction. And so this ends up being sort of a dominant source of heat transport in these planets. Okay, it's sort of the I'll get to it in some later slides, but this is like a very important piece of chemistry, and this is something that people could not have predicted from stars. And that's because in stars, it's like a star is like a spherical cow, right? Like the entire star is basically the same temperature at different locations, which means if the temperature is hot enough to rip apart your hydrogen into atomic hydrogen, it's doing that everywhere all the time. So you don't worry about this. But on a tidally locked planet, right, in synchronous rotation, the gas is flowing from the day side to the night side. And so this parcel of gas, every day or so, it's going all the way around this object. And so it's being ripped apart, recombined every day. And so that's actually exactly analogous to what water vapor does in Earth's atmosphere, right? Water vapor, you basically dump a bunch of heat in the ocean, you evaporate water, that takes a huge amount of energy. Okay, and now you have this energy that's sort of invisible. It's not sensible heat, it's latent heat. And then you can transport that water vapor somewhere else, and you can have it condense and rain down, and then you're basically releasing the heat there. So exactly the same process is happening. The energetics are orders of magnitude greater because you're actually ripping apart molecules, not changing the physical state of a molecule. But on the other hand, the temperatures involved are much higher. So it basically comes out in the wash, and it ends up much like in Earth's atmosphere, water vapor. The latent heat of water vapor is responsible for roughly 50% of heat transport in Earth's atmosphere. Turns out on an ultra-hot Jupiter, ripping apart hydrogen and sticking it back together is responsible for something like half of the heat transport on these planets. Okay, right, and again, transits are going to probe the terminator, eclipses probe the day side. Those have different, basically they could have like very different, not even abundances, but just like different states of matter, right? And so you could have ionized gas and atomic gas on the day side, molecules at the terminator, and then the night side, which I haven't really talked about yet, but the night side could have clouds, right? So you could have silicate clouds and things on the night side. Okay, so speaking about the night side, if you want to know what's really going on the night side, you have to observe the phase variations of the planet. So now you're not observing at transit or at eclipse, you're observing sort of like all the rest of the orbit. And so if this hypothesis about hydrogen dissociation and recombination is correct, then basically we expect the night sides of these ultra-hot Jupiters to be warmer than we otherwise would. Okay, so the normal expectation, if you ignore hydrogen dissociation, you get this dashed line where the night side is very cold. And the reason for that is that these planets are hot, which means that your radiative timescale is very short. And if you have a short radiative timescale, basically the energy gets absorbed on the day side and you immediately re-radiate it on the day side. And so then even if you have winds that are like Mach 1, right? So you have like winds that are on the order of the sound speed, they can't successfully transport heat to the night side. So you expect phase variations that are very extreme. When you're seeing the night side of the planet, you get very little flux. When you're seeing the day side of the planet, you get a lot of flux. On the other hand, if you account for hydrogen dissociation and recombination, you get much more muted phase variations. This is an exaggerated case, to be clear, but like I forget what wind velocity we had for this, but it was something ridiculous, like 10 kilometers per second, which is like Mach 3 or something. But the point is that if you have this extra way to transport heat, you tend to cool the day side and warm up the night side, because you have this new way to transport heat from the day side to the night side. You don't just heat up the particles of gas, you actually change the state of the gas. Okay, I think that was all I had to say about that. Oh yeah, why did I bring, oh yeah, okay, good. Now I'm gonna talk about Spitzer observations very briefly. So Spitzer doesn't work anymore, but we loved it. Those of us who worked on it loved it back when it last did. So this is actually looking at a bunch of night side temperatures of hot Jupiters, okay? So the y-axis is actually easier to understand. This is actually like based on Spitzer measurements, how hot is the night side of the planet? So each of these dots required an actual phase measurement. So in each of these dots, we actually observed the planet for an entire orbit. We or someone else. This is sort of a, not an anthology, what's the word? Anyways, this is a summary of a lot of people's work here. So that's what the y-axis is. The x-axis is essentially the radiation temperature. You can just think of it as an equilibrium temperature. It's like how much, how hot do I expect the planet to be given the amount of flux hitting it? So in general, to be clear, the trend you expect is that a planet receiving more flux, so a planet on the right side of this plot, you expect maybe the night side to be hotter. And so what you see is that there is kind of a general trend, but you can kind of, if you squint at this long enough, or arguably if you squint at this too long, you start breaking it up into two parts. There's sort of the run-of-the-mill hot Jupiters, where this line is almost flat, okay? And we think, well, this was a hypothesis we laid out in this 2019 paper up there, that what we're seeing is night side silicate clouds, okay? So essentially the story here, the story would be that the reason all these planets appear to have the same night side temperature is not because their atmospheres are actually the same temperature. It's that what we're seeing on the night side is a cloud deck. We're seeing the top of clouds. And this happens on Earth. If you look at the tropics on Earth, often the temperature that you see in the infrared will be basically, well, I don't know, I can't do it in terms of temperature, but in terms of like flux, it comes out to about 220 watts per meter squared, okay? So this is, on Earth, this is referred to as the FAT hypothesis, the fixed anvil temperature. These are called anvil clouds. These are big clouds you get in the tropics due to convection. They're all water vapor clouds in the case of Earth. And they always radiate at the same temperature, because basically by definition, the clouds condense at some temperature and pressure, and then they get lofted up. And then what you see at the top of the clouds is always this sort of, equilibrium value, regardless of how hot the surface is below. And so we think maybe we're seeing something similar on these normal hot Jupiters here, where the night sides would be covered in these, in this case, not water vapor clouds, but silicate clouds, so that the night side temperatures would always appear to be roughly the same, because they're basically covered in clouds. People have subsequently revisited this hypothesis with more nuance, and they've run general circulation models, and they think actually what might be happening is that you're going from totally cloudy to like the clouds breaking up and getting more and more sparse, and then eventually you get to like more cloud-free scenarios over there. Anyhow, so that would be the scenario for the kind of the hot Jupiters. And then when you get to the ultra hot Jupiters, which again, I'll take off the stupid cartoons, you can actually see better. Once you start getting up to these temperatures here, they're hot enough that you're going to start ripping apart your hydrogen on the day side, recombining on the night side. And so now you have this new mechanism for transporting heat to the night side. So your night sides get hotter, and they get, in fact, hot enough that you can't condense silicates on the night side. So you get cloud-free atmospheres even on the night sides of these planets. And then the temperature kind of shoots up. And this is the most extreme of the hot Jupiters. Okay. So this is my like hot Jupiters are complicated slide. which is basically the way we try and convince time allocation committees that we should still keep observing hot Jupiters, even though we've looked at them a lot, because we don't actually understand all the things going on yet. So, okay, so this I just mentioned, the isothermal night sides, maybe that's a sign of aerosols on the night side. I didn't have time to talk about this, but usually that we see winds blowing to the east on these planets, but every once in a while, and now there's like a growing number of these, like 3 or 4 planets, we see the winds blowing the wrong way. We don't know what's going on with those planets. It could be due to clouds on the day side, could be due to magnetic effects, which is really scary because there's very few people who can actually run a general circulation model accounting for magnetic effects. Arguably no one actually, but people are trying. There's this molecular dissociation happening. And then I haven't even mentioned disequilibrium chemistry because I kind of dodged this bullet by saying I was going to talk about hot atmospheres. So if we just define a hot atmosphere to be kind of like 1,000 Kelvin and hotter, then I can sort of ignore disequilibrium chemistry-ish. Except people have run fancy models like this, and it turns out some of the hot Jupiters I showed you, we actually do expect disequilibrium chemistry, which I find horrifying. And so I'm not going to talk about that. Okay, and all of this, I'm just using one arbitrary axis here. This is basically the temperature, the equilibrium temperature of the planet, like, cooler to the left, hotter on the right. But there's lots of other important parameters that, like, we know these should matter. Orbital eccentricity, on eccentric planets, these numbers aren't static. An eccentric planet is going through seasons. The orbital period matters because it changes the Coriolis forces on the planet. So if the planet's on a short period orbit, it rotates on its own axis faster, which means the Coriolis forces are stronger. The effective temperature of the star matters because that changes the incident spectrum, right? So if you orbit an M dwarf versus a G dwarf versus an A star, your effective temperature of your star is going to change where energy is absorbed in your atmosphere. Metallicity of your star and the planet is going to matter, et cetera, right? So basically, the moral of the story is that, like, we're still just scratching the surface of how hot Jupiters work, which is why we need something like Ariel, right? And again, I know you're all excited about Ariel as much as I am, so that's good. Okay, so that's sort of the motivation. Like, even if Ariel could do nothing but hot Jupiters, it would be awesome. We could just, like, give me phase curves of like 300 hot Jupiters. I'd be a happy man. Okay, maybe I'll go back to this and see, does anyone have any questions about hot Jupiters? Because I'm about to completely change gears.
I got one.
Yep.
When you mentioned like the latent heat, like the heat distribution and transport related to the dissociation of H to H. Is there anything coming from oxygen as well? Because you mentioned like water vapor is the other molecule that thermally dissociates. Do we have to account also for anything in terms of heat that comes from O2 versus O, recombine and stuff like that?
No, this is a super good question. So there's 2 things going on. So there's just a lot more hydrogen, right? So basically, just like in that sense, for a hot Jupiter, if you deal with hydrogen, you're basically doing a pretty fine job. But then you can imagine, okay, what if I go to a lava planet, which I'm going to talk about next? You can imagine some weird scenario where a lava planet somehow ends up with just like a whole bunch of oxygen. So you have an oxygen-rich atmosphere. And in that scenario, I actually put an undergrad on this because I was curious. And it turns out, and I apologize if there are any like molecular chemists in the room because I'm just going to really screw this up. But it has something to do with the like pound for pound hydrogen. You get a lot of energy. It takes a lot of energy to rip apart hydrogen, and you get a lot of energy when you recombine it per kilo of hydrogen as compared to, say, oxygen. So we did this math, and there's something to do with the size of the atoms and something about electron orbitals and fuck, I don't know. Anyhow, but like we did the calculation for oxygen and it wasn't nearly as impressive. So a pure oxygen atmosphere, dissociation will happen, but does it matter? Not as much as for hydrogen.
So it's just important to account for the chemistry, like just not to miss.
Yes, yeah, absolutely. Yeah, it's very important. Yeah, because otherwise you're like, hey, where's the water? And you're like, well, maybe it got ripped apart or something like that. Yeah. And then obviously you get different, I mean, my gosh, like maybe at certain wavelengths, you'd actually start worrying about seeing like oxygen. I guess oxygen doesn't really make very interesting lines. Yeah, so I'm not sure. But yeah, so it's important for the chemistry. And I think a lot of spectral retrieval codes can now account for this. But energetically, taking care of the hydrogen is good enough. Yeah, other questions about hot Jupiters? Okay, well, if something comes up later, you can ask later. It's also good. Okay, so now I'm going to talk about lava planets. So these are kind of my I've gotten really excited about these recently. I don't even, yeah, anyhow, lava planets, they're just amazing. So these are, instead of being a Jupiter that's really hot, it's the same thing, but it's a rocky planet. Okay, how do we know it's rocky? Because we see them transit, we see them with radial velocities. We can measure their mass, and we know that they have basically the bulk density consistent with being made out of rock. How these planets formed, again, super good question. I'm not really going to talk about that. But somehow there's this rock that's orbiting its star every day, sometimes every 6 hours. And so let's start with a basic question. Do these planets have atmospheres? In other words, do I have a right to talk about these planets in a talk that was entitled Atmospheres of Hot Planets? So the first thing we know is that a lava planet has to have a magma ocean, okay? And that's basically because the day side, so again, we're talking about a synchronously rotating object, so the night side is on the right, the day side is on the left in this case. These are rays of light coming from the star. Notice I didn't have them all come in parallel. I kind of exaggerated it, but this is a real effect because these planets orbit so close to their star that the star is like that big in the sky, right? Which basically means that there's no longer parallel rays. You don't have an illuminated hemisphere. You have about 2/3 of the planet is actually illuminated. All sorts of things are just, our normal assumptions just break down for these objects. Okay, but the point is, if we just calculate some naive equilibrium temperature locally at any region on the day side, the local surface temperature is hot enough to melt rock. Okay, so they have to have molten rock because we know their abundance, well, we don't know exactly what they're made out of, but they can't be made out of like hydrogen or ice or anything. Like just they're given their density, they're basically balls of rock like the Earth, which means on the day side, you have to have a magma ocean. So that's the first thing. If you have a magma ocean, then you have liquid rock. You can't just have liquid rock and then vacuum, okay? Like nature doesn't do that, right? So if you have liquid rock, there has to be a little bit of rock vapor above it. Okay? Just like if you have a glass of water in your room at night, or some, people put them on a radiator, you can get some water vapor evaporating. It keeps you from getting a bloody nose in the wintertime and stuff. So there's actually a little bit of rock vapor here, and it's small, but it's not zero, okay? So the pressures here are not going to be, on 1 atmosphere pressure, but you could have things that are like 1/10 or 100th of an atmosphere of pressure of rock vapor, okay? So the good news is these planets, we know they have to have a day-side atmosphere, okay? So that's good. So at least I'm allowed to talk about it today. People have known this for a while. The other cool thing to know is that the amount of atmosphere you have is going to depend sensitively on where you are on the planet. If you're at the substellar point, you're receiving the most light, it is hottest, you're going to get the highest atmospheric pressure here. And the atmospheric pressure is going to drop as you move towards the night side because the light is hitting you at a more glancing angle, which means your equilibrium temperature is lower, which means your saturation vapor pressure, which is what we basically care about, is lower. So you have high pressure to low pressure, which means you're going to get winds blowing this way. The winds are going to blow towards the night side. All right, and this has been known for a while. And I should mention, I don't think I have it anywhere on my references, okay, but this idea goes back to Andy Ingersoll in the solar system from a long time ago. He was thinking about the icy moons and things like that in the solar system, objects like Pluto. And he did all this math in the context of like nitrogen ices and nitrogen atmospheres. So people have known this since like the 60s and 70s, right? That you could get weird objects where you have an atmosphere locally, and then you're going to get basically supersonic winds blowing through vacuum to the night side, and it'll condense out. So basically all that people, like the first people who revisited this in the context of lava planets, which are Keston and Manu, all they did was just repurpose these old equations from Andy Ingersoll in the solar system and then said, okay, we'll do this for silicates, which was an extremely clever idea. Okay. I already mentioned this illumination pattern is weird. Okay, so you have something like 2/3 of the planet is illuminated. The penumbra region is enormous, right? So if you like sunsets and sunrises, you're lucky because on a lava planet, about 1/3 of the planet sees the star partially occulted by the horizon. And the night side is only about 1/3 of the planet. The night side is there, and on the night side, you don't see any of the star. Again, I should give credit where credit is due. There's an old paper by, I don't know, some Eastern European dude maybe, named Kopal, who did this in like the 1950s in the context of binary stars. Okay, so this was, again, people worried about weird scenarios like this. We have like a big star and another star, and they're orbiting like literally just like a 1 or 2 stellar radii from each other, and worked all the geometry out analytically. It's all like Legendre polynomials and stuff. So it's beautiful. And then people have kind of rediscovered it in the context of lava planets. Okay, blah, 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 temperatures. Okay, right, so the day side is hot, 3000 Kelvin. You get around to what you would call your terminator. It's 1600 Kelvin. And then the night side could be really cold, okay? Because the night side has not seen sunlight in billions of years because the planet is tidally locked in this permanent state. Okay, so some basic stuff. So this is work done by Zhang Wen, who's now a postdoc in my group. This is work he did as part of his PhD that I co-supervised. So this is an example of one of these calculations that are like, super old school, one-dimensional hydrodynamic calculations, very idealized. So this is atmospheric pressure as a function of distance from the substellar point. So 0 is like the star is right overhead, and then 90 degrees, the star is kind of like on the horizon. And then over here, you can still see part of the star because remember the star is enormous. And so even once the center of the star is below the horizon, you're still being illuminated. You still have a temperature of over 1000 Kelvin. And different abundances. And really the key takeaway here is that the y-axis is on a log scale. So the temperature, the surface temperature and the atmospheric pressure are dropping precipitously as you move towards the night side. They're dropping by orders and orders of magnitude, which means the winds are really strong. So the winds are going to actually accelerate towards the night side. So the winds blow, they start at the substellar point, they blow towards the night side and they go faster and faster. They easily exceed the speed of sound. You can see the Mach numbers here, 10, 20, 30 times the speed of sound. So the wind is basically just like expanding in vacuum, right? So you shouldn't think of this as like a wind on a planet. This is almost like a solar wind, right? Where you hit this like transonic point and now the wind's blowing away. But it's like that, but in spherical geometry on the surface of a sphere, because gravity is holding the wind to the surface of the planet. Okay, so now what I just said in cartoon form, the hot place is here. You're gonna get this rock wind that's blowing towards the night side. Eventually that rock will start condensing. As it cools, you're gonna get rock rain, rock snow, which you might call dust. And then of course, you can't just keep removing mass from the substellar point and dumping it over here. That like eventually that will lead to like a non-spherical planet that just breaks everything. So eventually there has to be some return flow. And so the general assumption is that that's happening through the magma ocean. So the magma current is flowing back towards the substellar point, okay? So this is really weird. It's sort of analogous to the water cycle on Earth, just in rock form, right? But it's the same idea. It's like you have evaporation in the tropics and then Hadley circulation, condensation, yeah.
Is this something that can be simulated numerically, like the existence of this magma, this return magma current?
We're working on it. Yes, ask about this again. I can talk more about that a little bit. So far, I'm talking about the atmosphere, and then later I'm going to talk about what's going on in the interior of this object, and we're just getting to the point where we can run dynamical simulations of it. Yeah.
So what do you mean with rock snow? So I may understand what the rest.
Oh well, rock snow is that it condenses into a solid form, and then rains down. This is actually, honestly, I think it mostly is rock snow rather than rock rain. It has to do, with where you are on your phase diagram, right? So like on Mars, for example, you get carbon dioxide snow, but you don't get carbon dioxide rain, just because of where you are on your temperature pressure diagram. So I think if you do the math, which Zhang, my postdoc, has done on a lava planet, you're mostly getting rock snow, not rain. But at some point, I made this cartoon and haven't changed it since. Okay, so now what are some of the other things that matter here? One of them is so your atmosphere. Let's pretend your atmosphere is made out of SiO, so silicon monoxide. There's reasons for this, which I won't go into right now. But if you're interested, you can ask me like, why not sodium? There's way more sodium. Blah blah blah. But we can talk about that later. Okay, so we have reasons to believe the atmosphere is going to be principally made out of SiO. And the problem with SiO is that it's got a freaking weird spectrum. So people who worry about hot Jupiters know this, right? So it's extremely absorptive in the ultraviolet, pretty much see-through in the optical. So you would just see the surface. If you looked at one of these planets, you wouldn't even see the atmosphere. You might see some clouds. but you would basically see through the atmosphere and then you'd see the surface. And then in the infrared, the opacity actually goes back up. So you get a weak greenhouse effect, but mostly the thing that's important about SIO is that it's really good at absorbing ultraviolet light, which basically means that you're going to get a really strong temperature inversion on these planets. In fact, okay, let's see, which of these, the top panel is the same as before. So this bottom panel now, we've got the surface in solid green. Okay, so that's the sort of radiative equilibrium temperature, more or less, because essentially the atmosphere is see-through, so the sunlight is just hitting the surface. But then if you account for the infrared and especially the ultraviolet opacity of the atmosphere, of the silicon monoxide atmosphere, you find that the atmosphere starts at 3000 Kelvin, and then it just stays at 3000 Kelvin all the way until the atmosphere dies. It just fully collapses out at 90 degrees from the substellar point, so around the terminator. Okay, so what's going on here, I think I have a box explaining this, is that the atmosphere here is being heated by ultraviolet radiation from the star, and it's trying to cool in the infrared. But because the opacity is so much greater in the UV than in the infrared, it ends up, the atmosphere heats up until a tiny amount of its blackbody radiation peaks into the UV, and that's how it cools, which is a weird scenario. So these kinds of scenarios, like people talk about this for like the solar corona and stuff like that. But here we have basically the same radiative transfer happening on a rocky exoplanet. So this is weird, right? So basically means that the temperature of the planet, of the atmosphere, doesn't necessarily track the surface anymore. It's going to remain really, really hot. So the entire day side atmosphere might be at like 3000 Kelvin. Okay, so that's all stuff that Zhang has already done. The next steps for him are, this one he's already done. Turns out that the story I just told you about UV absorption depends sensitively on your stellar spectra. So you need like really good stellar spectra in the UV, which anyone who works in this business will know that's not actually trivial. We don't actually have good UV spectra for most of these stars. So you're like looking for like, what's a very similar star to this? And I'll try and pretend they're a twin. And you need really good opacity tables for SIO, which actually have changed in the last few years. So like the group at University College London came out with like new tables of opacities, and you're like, oh crap, like that actually changed our answer. Okay, so that matters. We're trying to account for clouds now. We're trying to see what happens if SIO recombines with oxygen and condenses into little cloud particles. What would that do to all of this story? Turns out it's very hard to do this in your simulation and not have it crash, but Zhang is making progress on it. Mixtures of gases. So everything that I've shown you here is we do a single gas at a time, and we can kind of track what its atmosphere would do. But the reality is likely that there's going to be a mixture of gases. At the very least, you should have SiO and oxygen so that you have something to recombine to make SiO2, which is the rock form of this. So we're trying to figure out how to get mixtures of gases to not break the models. And then Coriolis forces, right? So the planet that we've been using as our poster child for all this is K2-141b, which has an orbital period of 6 hours, which means its rotational period on its own axis is 6 hours. And this is a super Earth, right? It's bigger than the Earth, which means at the surface, you're turning on your own axis 4 times faster than the Earth for a larger surface, which means the Coriolis forces are significantly stronger than on Earth. The velocities we're talking about are enormous, right? Because you have winds that are like going faster than the speed of sound, which means you can't actually neglect Coriolis forces. Like, the only reason we've gotten away with neglecting it is because the problem is hard enough that no one could figure it out with Coriolis forces. Then we could like write some papers without Coriolis forces. But at some point, like someone should figure out how to hack this code to make it work with Coriolis forces. So this is like the most challenging of these things, which actually requires like basically writing new kinds of hydrodynamic codes, which is not what I do. So I'm hoping to collaborate with real hydrodynamicists. Okay, now very quickly, what has Spitzer told us about lava planets? Spitzer tells us that lava planets are hot, which is what we expected, so that's good. This is work by Sebastian Siba, a grad student working with Laura Kreidberg at MPIA. So there's really not much that we can learn from Spitzer, basically because the error bars are freaking enormous, and it's photometry. So it's great. Like we know that the day sides are actually hot. You can actually get phase curves, right? So Sebastian published this phase curve, and it's fantastic that he was able to get a phase curve. I mean, the amplitude of this thing is, is like less than 100 parts per million. So it's very impressive as a kind of a technical feat, but it's really hard to learn much from this phase curve other than like, yep, the day side's hotter than the night side, but how much hotter, we don't know. Like, is it possible that the night side, has no atmosphere as we expect? We don't know from these data. So the thing to do is to look at this with James Webb, which fortunately is happening. This one planet, K2141b, is going to be observed this summer with 2 instruments, one led by my former PhD student Lisa Dang with MIRI, and the other one led by Nestor Espinoza with NIRSPEC. And so hopefully we will know soon what this planet actually looks like. And with James Webb, we're going to get way better data. Okay. I might finally be getting to answer to Matteo's question. Okay, so how deep is the magma ocean on a lava planet? Okay, so here's a phase diagram. So this is a phase diagram so this is pressure. So pressure is increasing going down. So you can think like the surface is at the top. And then this is going down into the planet. I have it for a super Earth-sized planet, so something like K2141. You can see kilometers going down. This is for an Earth-sized planet. Right, the size scale is slightly different because really what we care about is pressure. That's what determines the phase, and then temperature here. Okay, so let's see. Oh yeah, and then there's one more thing I have to explain is that silicate rocks, because it's a mixture of different materials, doesn't go straight from molten to solid. There's this partially molten state. Where you have, some components are going to start melting, but not all of them. So you can have a mixture of crystals and melt here. And this partially molten state is very, very important for a number of reasons. And this is something that we are not used to from things like water, because like water just goes straight from being molten to solid. Of course, water is weird in other ways, but anyhow, yeah. So for rocks, this partially molten state is important. And so now here are some possible kind of geotherms. So think of this as like a temperature pressure profile, but instead of being up in an atmosphere, now we're going into the interior of the planet. So if you're at the substellar point and you follow an adiabat, okay, then you're going to follow, so the substellar point is at 3000 Kelvin, and you're going to follow it down, and essentially your line is going to parallel these phase transitions, which means you're going to be in the liquid molten state all the way down to the core. Likewise, if your temperature starts in this partially molten region, you're going to basically stay in there. Okay, and the reason for that, it comes back to the same concept of latent heat. Okay, when you go through a phase transition, when you start partially melting or partially solidifying your material, there's a lot of latent heat, and that buffers your temperature pressure profile. So exactly the same reason that in Earth's atmosphere, water vapor, the presence of water vapor tends to give you, it improves vertical heat transport, so in a convective cell, which basically gives you a more isothermal temperature pressure profile, okay? And this is exactly the same thing, but going down in the interior of the planet, okay? So you have these TP profiles, and they basically, very few of them ever go into the totally solid region. In other words, our expectation might be something like this, that the magma ocean is not just this thing that's like, 10 or 100 kilometers deep. It might be thousands of kilometers deep. It might extend all the way down to the core mantle boundary. All right. So the magma ocean might be actually the entire mantle might be molten. And then likewise, you'd have this mush region, which is this mixture of solid and molten crystals. And then maybe the night side is entirely solid. Okay, so this is work done by Shed Boukhari, who's a postdoc in Paris, but who collaborates. He's a serial collaborator, one of my favorite geophysicists to work with. He lives in Montreal most of the year, actually, so it makes it easier to collaborate with him. Yeah, okay, so I just told you this, day side, blah, blah, blah. Yeah, and that word mush is actually like a technical term in geophysics, just so you know. Like, I didn't make that up. It's basically like slush, for those of you who are familiar with that.
Sorry, can you explain again why all the mantle could be molten? Sorry, I missed that. Not just
No, it's just, it's basically because, like, so the naive way to think about this, which is the way I previously thought about this, is let's say I'm at the surface, and let's say I'm at the substellar point. The surface is 3000 Kelvin. And then I figured, okay, I'm going to go down to higher pressures. Then I eventually hit some place where it becomes partially solidified, and then by 40 gigapascals, which is like 300 kilometers down, I should be solid, right? So my original way of thinking about this was like, okay, at the substellar point, if I go down a few hundred kilometers, I reach solid rock. The problem with that is that I'm assuming an isotherm. I'm assuming that as I go down into the rock, it stays the same temperature. But that's not the way planets work. Like if you dig down a deep, deep tunnel on Earth, it gets hotter, right? Because heat is trying to get out from the Earth. And the core of the Earth is still like the same temperature as like the surface of the sun, right? The core of the Earth is still at 5,000 or 6,000 Kelvin, right? It's like very hot down there. So that heat is still trying to get out from back when the Earth formed. On a lava planet, it'll be the same problem, but even worse, because it's even harder for this planet to cool than it is for the Earth to cool. Okay, so basically the core mantle boundary is 6,000, 7,000 Kelvin, and so the way you're not really going down to higher pressures, you're going down to higher pressures and higher temperatures as you go down, and so you never intersect the phase boundary basically. So that's why it ends up being liquid the whole way. Does that make sense?
Yes.
Okay, cool.
Thank you.
Okay, composition of the lava planet's magma ocean. So yeah, what do we expect this thing to be made out of? Okay, so in the fully molten place, in principle, the story is simple because you take the full mantle, you melt it. So there's actually on Earth, there's a name for this. It's called the bulk silicate Earth, the BSE. So people who study the Earth, you've probably seen this like when people are doing like cloud compositions on hot Jupiters. They're like, what's a typical rock? And they take a bulk silicate Earth composition. So you just take the entire mantle, you melt it, and then your atmosphere here is going to be, again, just the saturation vapor pressure. So you want to know, like, okay, how much sodium do I have? And you say, well, how close to saturation? What at this temperature, what is the saturation vapor pressure of sodium? And then you say, okay, well, that's the pressure of sodium I'm going to get. And you do this for each element individually. Okay, so on the fully molten region, it's fairly straightforward. In this mush region, it's a mess. Okay, and that's basically because as I progress more and more into the molten region, what's happening is certain elements prefer to be in the solid crystals that are forming, and certain elements prefer to stay in the molten stuff. So for example, anything that you think of as a volatile, which includes actual volatiles like water, but also things like sodium and potassium, will prefer to be in the molten thing, not the solid thing. Okay, which means that they get more and more concentrated in the melt. And then eventually the melt becomes saturated in water, sodium, potassium, et cetera. And then at that point, it just catastrophically degasses into the atmosphere. And if you're kind of like keeping in mind the sort of geometry of all this, that means that your volatiles might preferentially get degassed right in this region, which is basically the terminator, which is like, that could be cool, right? Like maybe we could do transit spectroscopy on this. It would still, to be clear, it'd be freaking hard. Like if you do the signal to noise calculations, it's hard, but maybe it's not impossible. Like maybe this is something that like ELT could do, or maybe VLT between now and then. We'll see. Okay, right. So this is like this was a cartoon at the end of Charles Edouard's paper, kind of because we did everything in a kind of a static way, but he's a fluid dynamicist, so he does like fluid dynamics of magma oceans, and so we need to put arrows somewhere to kind of like suggest that all this shit's actually moving around. So you have this fully molten region, you have upwelling at the substellar region. If nothing else, you have to have upwelling here because you're evaporating atmosphere, so you're losing mass. You have to replace that, so you're flowing up here. Then you have this flow towards the night side. And then at some region somewhere, things have to start coming down. We weren't sure where it was. And then we said volatile degassing, because maybe that's happening in this partially molten region. Okay, there's a lot of work to be done on this, and this is all work in progress. So Shed is actually writing a follow-up paper where he's actually done two-dimensional models that look very similar to what I drew there, like these kind of box models, and three-dimensional hydrodynamic simulations. And let's see, some of what I told you here is correct and some of it is totally wrong. but basically, it turns out you can't have a planet with these very different states on it in equilibrium. if you have this deep molten part here, it'll transport enough heat to keep the entire planet molten. So essentially, either the lava planet is fully molten, even on the night side, which is weird and has observable consequences, or it becomes fully solidified, and you actually end up with this very thin magma puddle on the day side. Okay, it's kind of like this bistable thing. Yeah.
One thing you didn't mention is like, what about tides? Because the quality factor is going to be different on the night side and the day side. Like if you have a molten part of the planet and it's solid.
Yes.
Does that matter? Does it need to be considered?
Yes and no. Yes, if you wanted to worry about tidal dissipation in a lava planet, it would totally matter. And this is at some point I tracked down someone at a workshop who does tides, and I told her, like, please work on this, it'd be so cool. The problem is, as she pointed out, that tides only matter if the planet is not synchronously rotating. Like if it's actually really in a circular orbit and synchronously rotating, there is no tidal dissipation anymore because it's a static tidal kind of deformation. So in that case, you don't care about it. But if these planets have companions, and it turns out they all have companions, so they're probably all getting yanked around a little bit, and so probably tides are happening, and someone should work on that. Yeah, like maybe, and as you could imagine, the tidal dissipation is like, yeah, it's a very weird problem, and the planets are on such short period orbits that if there's tides, the entire planet's gonna get molten or something crazy like that. Yeah, but no one has worked that out yet. But again, it only matters if they're not on a perfectly circular orbit. Okay, so anyhow, so yeah, these hydrodynamic simulations are coming out. And then the other thing is that Shed Bukhari and I are co-supervising a PhD student, Mahesh Herath, who's working on the long-term thermal evolution of these planets, exactly in the hopes of getting to questions like, you know, would tides matter? Like, when did this planet move in here? Some of these lava planets are only like 1 billion years old. Some of them are 10 billion years old. Does it matter? Like maybe for the first billion years, the planets are actually fully molten, and the night side is this like thin little crust that keeps floundering and sinking into the magma ocean. Or some of these planets might be fully solidified. Like we'd love to get to the bottom of this. Again, James Webb observations would be super useful for this, but in the meantime, we're doing theory. Okay, so summary: hot Jupiters are still really fun. So back when people discovered hot Jupiters, I think the expectation was like, these are gonna be so easy because they're basically solar composition. And I don't know, I think there was just like this naive hope or expectation that hot Jupiters would be simple and easy. And yet we keep finding surprising things about them, and there's a lot of things we don't understand about them. So we should keep observing them. And lava planets are a fantastic way to track down your like geophysics and geology colleagues and say, hey, like, let me tell you about something really cool. Maybe we could collaborate. Okay, I think I'm ready for questions now. Thanks.
Thanks. This is really spectacular. Any questions from the audience, and then we'll check if there is something that will be online. Please first.
Yeah, excellent stuff for the lava planets. For the part what you want to study the evolution of this, what are your sort of hopes or expectations? Because I remember for people studying plate tectonics that this is not a simple process, there are hysteresis problem where the thing is not entirely determined by the moment that you're observing or how it evolves. It changes with the history.
Yeah. So the answer, so maybe this will be a good answer, maybe it'll disappoint you. We're not trying to do anything as fancy as plate tectonics on this, because as you know, as you just pointed out, we don't even know why the Earth has plate tectonics. We don't know how far back in Earth's history we've had plate tectonics. So we're doing zero-dimensional models to try and understand the thermal history. It's a box model. You've got a box for the core, and then you've got one box for the day side mantle and one box for the night side mantle. And when you want to get really fancy, you split up those day side and night side boxes into two, because you have the potential for a solid part where you have solid body convection, like we have in Earth's mantle, and then you might have a liquid part, and obviously the convective motions are very different in those two, right? So you basically have like 1, 2, 3, 4, maybe 5 boxes total, but it's a zero-dimensional model. And it turns out people have never developed this, because in the Earth community, and in fact in the solar system, whenever people talk about magma oceans, it was always this very brief transient state, right? Like a magma ocean happened, like the moon smacks, the moon, like Theia, right, smacks into Terra, and that's what makes Luna. And after it hits, you melt everything. Oh, you have a magma ocean, but then it just solidifies really quickly. No one is ever worried about like a permanent, like what if the magma solidification front, like you solidify your mantle from the bottom up, what if that stalled at some point because of heavier radiation? This is just like, nobody ever had to worry about that before lava planets. So it's funny because on the one hand, the models are like ridiculously naive, but on the other hand, no one's ever done it before, which means like you write out all these differential equations and you're like writing them out for the first time. And so maybe this will be useful in the solar system, probably not, but like it's very naive, but it's because no one's done this kind of thing before. Yeah, God, like plate tectonics and stuff. Yeah, sure. Someone could do that, but honestly, I think like trying to run plate tectonics on like a partial sphere like this and then have this part all molten, I think there'd be so many problems with that. It's the same reason that no one wants to run general circulation models on lava planets. It just breaks the model. It's not useful. So we do very naive things instead.
Or maybe an impression. In your models of the atmospheres of lava planets, do you also take into account the possible interaction between the atmosphere and, I guess, a very strong stellar wind? Or is this interaction negligible?
I don't know that it's negligible. That's a super good question. Gosh. Yeah, no. The short answer is no, we don't account for this. And is it negligible? I don't know. So I did not really address atmospheric loss on these objects. In fact, I kind of cleverly avoided talking about atmospheric loss all day. And that's because I talked about hot Jupiters where it's like, who cares? Like if you lose a bunch of hydrogen, there's still a lot more hydrogen where it came from. And on these planets, everyone just assumes that they've already lost any volatile, like CO2, methane, carbon dioxide, carbon monoxide. Like you assume you've already lost all that to space. And then what you're left with is the things that can live in the rock. But as I noted in one of these slides, you rip apart SiO2, which is the form that silicon takes in a rock, and in gaseous form, it prefers to be SiO, which means now you got an extra O. And what do you do with that oxygen? It's either atomic or maybe it recombines with another one, and now you have molecular oxygen. Either way, you have oxygen. Oxygen is lighter. Atomic or even molecular oxygen is lighter than SiO. Could that oxygen be lost to space? Maybe. Could it be detectable with like some sort of clever spectroscopy? Maybe. I don't know. But like, yeah, nobody has done this super carefully, I don't think. And like naively, I would assume that if I have winds going at Mach 20 towards the night side, to me, that seems like it would be easier to lose some of that gas and that it never actually rains back down. Some of it just sprays off into space. Yeah, that would be a super fun. I don't know anything about that. That sounds great. We could talk more.
Can you come back, please, to the slide of Spitzer with the plot and point?
This one? Yeah.
Do you think that JWST could fill this plot and, for example, fix the degeneracy between the two temperatures?
Absolutely. Yeah. So James Webb is going to, like with NIRSpec, we're going to get this. And then with MIRI, we're going to get that. And the error bar is going to be way, way smaller because it's a much bigger telescope. Yeah, so the hope actually is not only will we get, better constraints on the temperature, but we might actually detect some of the spectral features of things like silicon monoxide. So we might actually confirm that, yep, this has a rock vapor atmosphere. That's the hope. Okay.
Any questions from the online participants? No, if there are none, I have also a question.
Yeah, sure.
Among the various elephants in the room that are probably there, one thing we are beginning to very much worry about is timescales of variability. Mm-hmm. In hot Jupiters, is there any expectation, any chance of considering that things at Terminator may look different on orders of rotation periods, of saddle rotation periods, or something that looks like not too geological in age?
Yeah, I mean, this is another excellent question. I did not mention variability here, basically because it's in the theoretical predictions. I would say it's a mixed the theory is that people have conflicting predictions about this, right? So most people who run general circulation models of hot Jupiters expect the variability to be very small, at the level of a few percent. There's one exceptional group who run kind of different higher resolution hydrodynamic simulations, and they've predicted, they predict very high variability. The problem with their predictions of very high variability is that that's inconsistent with observations of actual hot Jupiters, because we have repeated observations of like eclipses. There are certain planets where we observe them for like 10 eclipses, and the eclipse depth is always basically the same. We get very, very, very little. Phase variations have only been repeated a handful of times, and they're mostly consistent with each other. So we don't think that these hot Jupiters are varying that much, but it's hard to know because we haven't had very precise instruments, right? So at the level of James Webb precision, I fully expect we'll see variability. The easiest places to vary things, as you said, are either the terminator for transit spectra, because in that case, if you're seeing a thin little annulus, you only have to change things a little bit in a small local region of the planet. So it's conceivable that you can go from cloudy to cloud-free from one day to the next. And the other place where it's relatively easy to change things is on the night side, because the night side is a much lower temperature. So if you have a day where for whatever reason you have more efficient heat transport from the day side, it makes a big difference on the night side. Whereas on the day side, it's so heavily irradiated that it's very hard to change the temperature structure or anything on the day side. It tends to be just kind of like fixed. You're kind of like, you're smacking the gong so hard on the day side that it just always looks the same. But the night side of the terminator, yeah, maybe they vary. And like we know from looking at brown dwarfs, which are basically the same as this, just without a star next to them, we know these things have internal modes of variability. So yeah, I mean, probably all of these hot Jupiters are varying. It's just that we haven't been able to detect it yet. But with James Webb, maybe we'll be able to detect it. And this could be an interesting science case for Ariel, where you can like repeat observations of something over the course of months or years. Yeah, we'll find out, I guess.
Time for one more question.
Very fascinating, all of this. So the rocky winds especially are really fascinating. Is there some kind of, is it modulated by the rotation period of the planet in some ways, or you wouldn't see that because it's so supersonic?
Okay, wait, so wind, you want to know if the wind speeds should be connected to the rotation speed of the planet. Yeah, I mean, in principle, they should depend on it. So in the case of, okay, so I'll do both like hot Jupiters and lava planets, just because those are the two I talked about. Okay, so for lava planet, well, I'll start with hot Jupiters. Hot Jupiters, again, pretty much unanimous consent that you get equatorial superrotation, which basically means you get winds at the equator blowing in the same direction as the rotation, but going faster than the rotation. So even if the planet, you decide how fast the planet is spinning, and then you let the hydrodynamics run its course, and then the steady state is going to be at the equator, things are going even faster than that rotation. Which when you think about it is kind of weird. It basically means you're concentrating angular momentum in a place that already has the most angular momentum, which is not a natural state of being. Like on Earth, for example, if you go to the equator, we have trade winds, right? So we have winds blowing. Like this is how the conquistadors famously went to the Americas, right? Because they went down the African coast, and then you get winds blowing towards the west at the equator, which kind of makes sense because our planet rotates that way. You export heat away from the equator, you export angular momentum away from the equator. It's a diffusive process. You end up with a deficit of angular momentum at the equator. The winds blow to the west. So everything kind of makes sense for the Earth. For hot Jupiters, it's weird, but it's not unprecedented. So people see that on Titan, they see it on Venus. These cases where things, the winds blow in the same direction as the rotation and actually go faster than the rotation. So is there a connection with rotation? Like, yeah, in the sense that you're going in that direction and you're going faster than that. The other connection is if you make the planet spin really fast, the Coriolis forces get stronger, which makes your jets get narrower and narrower. So it becomes, so if you look at an object like Jupiter, right, it's got all these stripes, right? These are all the different zonal jets that switching direction because of Coriolis forces. On a hot Jupiter, most hot Jupiters, the Coriolis forces are weaker than on Jupiter because they're totally locked and they've got a rotation period of like, a couple of days. So instead of rotating on its axis every 11 hours, like Jupiter rotates on its axis every 50 hours. So the expectation is that the zonal jets on a hot Jupiter should be wider and they should be blowing towards the east. Okay, On a lava planet, no one's tried it. Like all we can do for a lava planet right now is we run one-dimensional simulation. So it's just like a piston on the surface of a sphere, and we're just like let the gas. I can't sound on that sound. Anyway, we let the gas go and it goes like that, and it just goes faster and faster. Now in reality, you're doing this on a rotating object, which means that as you move away from if you're trying to go over the North Pole, for example, as you move north, Coriolis forces are going to deflect you. Right, so you can't actually go up and over the North Pole. So what we tell ourselves that maybe what we're doing is like not terrible for winds blowing east and west along the equator on a lava planet. And it's on our to-do list to try and figure out how to account for Coriolis forces, to do kind of like a pseudo 2D simulation, like a 1.5 dimensional simulation. But yeah, that's on our list of things to do in the future. Yeah, no one knows how to do Coriolis forces for lava planets yet.
If there are no more questions and no one is actively asking online, I think it's a good time to thank again. Chris. Nick is here for the day, and now we'll take over for lunch.